Well, this tutorial is about the hyperbolic partial differential equation, and we will use the technique central time and center space derivative definition. So let's look at the problem. Partial square u partial t squared equal to 4 partial square u partial x squared, and the x has bound from 0 to 1, and the t is for all times greater than 0. So this is also a kind of propagation problem, and also it has the boundary values. The conditions for 4 conditions which are required to solve this hyperbolic PDE are as u0t and u1t. These are of course boundary conditions. Then we have two conditions, ux0 equal to sine of pi x. This is one initial condition, and the other is a derivative condition. This is also initial condition, and we call it a velocity condition. That is the nomenclature derived from the consistent with the wave equation. So it is one-dimensional wave equation. Here we define the derivatives. So if we look at the picture, the time is shown in the vertical axis and the space is shown in x-axis. So we have indices I for x and index j for the time. So when we define the partial derivative with respect to x, so it keeps the time fixed and only x variation is considered. So I minus 1, I and I plus 1 indices would be used. However, j index will remain fixed. So if you look at the definition, it will be ui plus 1j minus 2 uij plus ui minus 1j over h squared. So this is the definition of derivative with respect to x, second derivative in u, and we will use this approximation to define the derivative at the particular node ij. Similarly, when we differentiate with respect to time, a partial derivative, it will keep the x index same. So we will move along a line which is parallel to y axis. So our indices would be j minus 1, j and j plus 1, and I index will remain fixed. Okay, so you have that definition in this equation that has been pointed with the help of the spotlight. Now if we write these approximations to the equation, so we have an equation in which we can compute the value uij plus 1 by utilizing the value uij minus 1, ui minus 1j, uij, and ui plus 1j. Like the expression over here, this expression is specific to this particular problem. Here we do not have the index uij. This point is not there. That is due to the cancellation or the value of lambda. So it means a value at a point can be generated by using the values at previous 2 steps. So that is the problem, that we can only have the values at the previous step. So in that case, we use the velocity approximation. So when we define the velocity approximation, velocity value with the numerical approximation, and in that case we define with the forward difference form. So over here it is equal to 0. So value at the first time step can be computed. A value from a 0 time step to a value at the first time step can be computed. So you can see the detailed expression from the slides and notes. So that expression can be simplified to the expression over here, that ui at the first step would be equal to ui0. So it is going to be similar to the first expression. So let's do the simple computations. So I have developed a frame where we have with different colors are the identification of boundaries and initial values. And in order to be consistent with the demonstration, uh, let me make the figure consistent. I have to rotate this figure 90 degrees so that this is consistent with my definition. So that is going to be consistent with the stencil. Okay. So a value at this point will be in general a weighted sum of the values available at these points. And J index is increasing in the horizontal direction and X index is increasing in the vertical direction, however in downward direction. That is for demonstration in Microsoft Excel. So let's apply the initial and boundary conditions. So first boundary condition, for all times at x equal to 0, we have value 0, and the same goes for the right boundary condition at the other edge of the problem. So like the waves in the string, since I said it is similar to wave equation, so both ends of the string are fixed. So u0t is equal to 0. So let's make it 0. So we have 0 over here. This is one boundary. And the other boundary is here. It is also. So the value for all times, the time scale is over here. So time scale is varying over here. So I hope it is now more apparent. At t equal to 0, we have all the values 0. And for all times at the second edge, the position u is fixed. Now, the initial condition ux0 equal to sine pi x. So for all positions, the value should be computed as sine pi x. So I can write here sine of pi x, pi times x value. And similarly, I can generate the values for the rest of the points. So you can see the initial position of the string in the picture from 0 to 1. It is fixed at 0 and it is fixed at 1. So in between, the points are going to oscillate. They will perform the simple harmonic motion. Now at the first time step, t equal to 0.05, so we can use the velocity condition, and velocity condition suggests that ui1, since it is equal to 0, so we can have the values. Let me write. In a general problem, you may have some expression over here. Well, you definitely have some expression when the partial u by partial t is defined at x0, of course, is defined as a function g of x. Like we have ux0 equal to a function sine of pi x. So you may have partial u or partial t as a function of x. So over here it is 0, so we are more than happy. So the same values would be used. So we have the values available at first two time steps, and now we can implement the explicit equation, just like in the case of FTCS for parabolic differential equations. So I generate the expression, and graphs will be generated. We have to write that one just for once. So uij plus 1, this value. Let's again look at the picture. The value at a new point, a new value will be generated from the values available at two previous time steps. And in our case, we have rather more simple expression. So ui plus 1j, so this is the value over here. So I will write the expression consistent with this outlined expression. Uij plus 1 plus ui minus 1j. So on the jth step, and I'm doing the calculation in the j plus first step. Okay, and minus uij minus 1. So uij minus 1. So 3 points. In a general problem, we have to include this value as well. A simple sum that is required. Okay, so let's repeat the calculations, and our graphs will be updated, and then we can move ahead in time in the same fashion, and we can see that the waves are there. Okay. So this completes the tutorial on center time, center space problem with the boundary conditions, 2 boundary conditions and 2 initial conditions, where one initial condition is given in the at x equal to 0, the initial position of points, and the other condition is given as their initial velocity. So for the waves in these strings, generally we have that condition that their endpoints are fixed, their initial position is fixed. They are released from a 0 velocity, and then they oscillate. Okay.